Hello everyone, my name is Samuele Poppi and I'm going to present to you revisiting the evaluation of class activation mapping for explainability, a novel metric and experimental analysis. A work done with Marcella Cornia, Lorenzo Baraldi and Rita Cucchiara from the Image Lab laboratory at the University of Modena and Reggio Emilia. In this work, we develop a more solid and less biased benchmark for evaluating the results of the different class activation mapping methods. The first problem to tackle is what does explaining a CNN for classification mean? This has been solved in the last years by computing a relevance map, named size map of the input image, in which each position is numbered in 0, 1, and it represents the importance of the same pixel. From this, we can obtain the explanation map by multiplying pixel-wise the size map and the input image. This map will hide useless pixels and will show the useful one. To extract these maps, there have been defined different attribution methods that are basically functions attributing a relevance to each pixel. In the recent literature, there are three main approaches: gradient-based, perturbation-based, and CAM-based. We are going to talk deeply about these last ones. A CAM-based method is defined as a linear combination of the activation maps of the last convolutional layer. In other words, we feed forward an image into the CNN. We extract the feature maps output from the last convolutional layer. We compute a list of weights using a specific approach, and we'll come back on this later. Finally, we compute a linear combination between the feature maps and the weights. This results in the final saliency map. As it might be evident, all the CAM-based algorithms share the same global algorithm, but they differ in the way they compute those weights. Some of them rely on the gradient with respect to the class activation maps. Others don't use the gradient at all, and so on and so forth. But how are these algorithms evaluated? Some metrics have been recently proposed, and we have focused our analysis on them. All of them focus on the same concept: how high is the change of the model confidence induced by the explanation map. For instance, the average drop measures the average percentage drop in confidence for the target class C when the model sees only the explanation map instead of the full image. So, the model confidence of the plain image is recorded and compared to the model confidence of the explanation map. Obviously, the lower average drop, the better. The average increase computes instead the number of times the confidence of the model is higher when using the explanation map compared to when using the entire image. In this case, we are measuring the increase of the model confidence, and so the higher the better. But the metric only takes into consideration if the score of the class has increased or not, totally forgetting about the amount of the rise. Other metrics used to evaluate the CAM-based approach's performances are dilation and insertion. Dilation measures the drop in probability of the target class as important pixels given by the CAM are gradually removed from the image, while insertion computes the rise in the target class probability as pixels are added according to the CAM. Both metrics are expressed in terms of the total area under the curve. As it can be noticed, they are considering only the model confidence as well. But is model confidence the only affordable indicator of the performance of a CAM-based approach? Or can we do better considering maybe other aspects? Moreover, considering a set of different metrics makes comparisons cumbersome. It would really be better to have just one score. In addition, the average increase instead is way too discrete, and the average drop is a good indicator of the model confidence, but alone can easily lead to wrong evaluation. To give clear evidence of this last point, we built a fake CAM approach in which weights alpha k do not depend on the confidence score. In fact, for each activation map, fake CAM produces a weight alpha k in matrix form, in which all pixels are set to 1 over NL, where NL is the number of activation maps, except for the top left pixels, which is set to 0. So, constant saliency maps, clearly independent from any input image or any CNN. Obviously, in terms of explainability of the CNN, these saliency maps are totally insignificant, and the right metrics should give awful results. As we can spot in this table, our fake CAM is winning badly, reaching ideal scores in terms of both average drop and average increase. A little tweak addition, because the resulting explanation map is almost equivalent in the original image, except for one pixel in the corner which is unlikely to contain the target class, the average increase of fake cam is usually very high, surpassing 45% using most backbones. 45% of average increase means that almost in one image over two, the model confidence is increasing. Similarly, the average drop of fake cam is almost zero because of the high similarity between the input image and the explanation map. So, it was quite evident that the model confidence alone could not be a reliable aspect of CNN for classification explainability. So, we started analyzing what could be an ideal attribution method and which properties should be verified. Firstly, the attribution method should verify the maximum coherency property, and so, given an input image X and a class of interest C, the cam of X should not change when conditioning X on the cam itself. And this is like requiring that the saliency map computed on the plane image should not change when computed on the explanation map, as we are simply removing the useless input features. Secondly, the attribution method should verify the minimum complexity property, requiring the cam to be as less complex as possible, meaning that it should contain the minimum set of pixels that explain the prediction. With the L1 norm, we measure its complexity. Thirdly, as expected, the ideal attribution method should verify the minimum confidence drop property, producing the smallest drop in confidence with respect to using the original input image. To compute this property, we directly use the average drop. And finally, we combine these three metrics into a single score, computing the harmonic mean of the previous three ones. We call this score average DCC. Being a single valued metric, it makes very simple comparisons between approaches, and also it takes into account three different and essential aspects of an attribution method that weren't considered before. And here's our results, computed on an entire ImageNet 2012 validation set and on different backbones. As a first consideration, FakeCam is still winning in average drop and coherency, but it has a very high complexity, almost the highest possible, and so its ADCC score is the lowest among all the other attribution methods. As we can see here, it is highly evident how the average drop alone is definitely not enough. In fact, in the theoretical case, the best average drop score is in the smooth GradCam++ case, but its saliency map is very coarse, while the saliency map produced by ScoreCam is pointing better to a precise subset of input features. This really shows how powerful our ADCC score is. And this concludes my talk. Thank you very much for your attention. Hope you enjoyed it, and if you have any questions, please do not hesitate to ask.